bar elements with maybe 2 node, additional of 3 node quadratic element. Then we moved on to truss elements and beam elements, and we also entered into the 2D dimensional 2D analysis, where the 2-dimensional plate-like structures, triangular, quadrilateral, and all such type of elements we have studied, as well as the higher order elements in the 2D also we have studied now. But in most of the applications, even though we have studied 3-dimensional analysis in axisymmetric solids, but finally we converted axisymmetric solids into 2-dimensional problems only. So therefore, the real, you can say the analysis, most of the applications in engineering involve the 3-dimensional analysis, because most of the components which you are going to analyze in using your finite element analysis will be of arbitrary shape, it will be irregular shape, and we will be needing to make the complete 3-dimensional analysis only. So for that, we need to develop the new set of equations, because we have already seen as the number of dimensions increases, the stress, strain, and all other components are going to increase. We have seen that for 1-dimensional it is only sigma x, and in the 2-dimensional it was sigma x, sigma y, and tau xy. There were 3 strain components. When we went to axisymmetric solids, which is partly 2D as well as 3D, we added 1 more component. So there we had 4 stress components and 4 strain components. Whereas in this case, when we are talking about the 3-dimensional analysis, the stress at a point, if you want to define in a 3-dimensional object, it is always going to consist of 6 components. That is 6. Now all the 3 Cartesian coordinates, x, y, and z, we need to define sigma x, sigma y, and sigma z. At the same time, tau xy, tau yz, and tau zx. 6 components of 3 normal stresses and 3 shear stresses need to be defined with that. In the similar manner, we need to define 3 normal strains and 3 shear strains in the case of strains also. Here, naturally, when we are talking about 3-dimensional, the displacement of a point is going to be in 3-dimensional. Along the x, if it is going to move by a displacement u, along the y direction, it is going to be v, and along the z direction, it is w. So the third displacement component, which is w, is going to be added in this particular context. So therefore, we are today studying about the various, you can say, aspects of 3-dimensional problems like this. Generally, we use what are called as brick elements. These are called brick elements or solid 3-dimensional elements, which are going to be used, and in that mainly we are discussing most of this is tetrahedral element, that is a triangular tetrahedron with the 6 nodes. We are going to study this, and similarly we will be going for hexahedron and other elements. I will just introduce you how they are going to be formulated. So let us quickly go to what is this. This thing is, as I told you, displacement vector u is consisting of 3 components, u, v, and w transpose, and the stress component, again I told you, it is going to consist of sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. And the same manner, if you take the strain components, it is again 3 normal strains and 3 shear strains. These are the, you can say, components of this. If you want to express them in the partial derivative term, this is of course dou u by dou x, dou v by dou y, and dou w by dou z. Whereas when it comes to this one, it is dou v by dou z plus dou w by dou y. When it comes to the next one, dou u by dou z plus dou w by dou x. Lastly, dou u by dou y plus dou v by dou x. And these are all transfers. See, these are the stress components which are going to be 6 by 1, and this is also 6 by 1, and this is 3 by 1. These are the matrix sizes and all that. Now, how to relate? As usual, you know that stress and strain are related by the relation sigma is equal to C times epsilon. So naturally, this is 6 by 1. This also 6 by 1 means it has to be of 6 by 6 size. Okay. So we should use three-dimensional, you can say, material matrix C. Let me write what is that. It is going to be given by E upon 1 plus nu, 1 minus 2 nu, and here we are using 1 minus nu, 0, 0, 0, nu 1 minus nu, 0, 0, 0, nu 1 minus nu, 0, 0, 0. When the remaining are all zeros here, this is all 0, 0, zeros. These are 6 sets of zeros. This you can write it as 1 minus 2 nu upon 2, or in some cases they write it as, just write both of them for your convenience. This is written as 0.5 minus nu, they are writing. This is also one and the same. Half minus this, they can write that. And this is 0, 0, 0.5 minus nu. See, this is what is called as the material property matrix, which is of 6 by 6. So when this is multiplied to the strain component, 6 strain components, we are going to get the total stress, 6 stress components as far as this is concerned. Now when it comes to the body force, okay, body force vector, body force, this is again F. It is going to consist of 3 components, Fx, Fy and Fz. And in the similar manner, traction component. If you want traction, T is also consisting of Tx, Ty and Tz transpose. So this is how we are going to write. And you are already knowing the total potential energy in the 3D. We are going to write that. What is that? Total potential energy. That is pi. Is given by strain energy, which is over the volume, sigma transpose epsilon dV, minus it is over the volume U transpose F dV, minus as far as the traction is concerned is over the area. So this is U transpose T ds minus summation I Ui transpose Pi. So this is going to give you the complete picture about the three-dimensional formulation, how exactly it is to be done, and later on we can extract each component. As I have told you, from the strain energy we can extract the element stiffness matrix, whereas from this we will extract the body force component, that is body force vector, and the traction vector and the point loads. Like that we can simplify it later on. Let us start with now one of the element, one of the very, very common element which is used in finite element is tetrahedral element. Tetrahedral element, and we need to make the finite element formulation for this FE formulation. Okay, so let us quickly make a simple sketch of this. Let's designate the nodes 1, 2, 3, and 4. This is a 4-noded tetrahedral element with all the base as well as the 3 faces are being triangles. Okay, this is the face. We'll take this like this. Q4, Q5, Q6, Q7, Q8, Q9, Q10, Q11, and Q12. This is about this. This is the given, and here, as I told you, the coordinates of this are x, y, and z, and this is of course going to be u, v, and w, are the 3 components of forces which are going to be there. This is the origin. See here, you can see there in 3-dimensional analysis, every node has got 3 degrees of freedom at a particular point. One in x and one in y and one like that. If you totally count, there are totally 12. You can say displacement components are there. Therefore, if you want to note down this q vector small for every element, it is q1, q2, q3 up to q12. Okay, transpose. This is going to be a 12 by 1 matrix. Okay, and it has got a base as a triangle, and all the 3 faces are also isosceles triangles, and this type of 3-dimensional body element can be done that. So naturally, when we have 4 nodes, we need to define the 4 shape functions. Okay, so therefore we define them into number of elements and the number of nodes. When we write, let us write the connectivity table for this. Let me write the connectivity table. Connectivity, we'll write that. This is the element number, and here we have 1, 2, 3, and 4. We have, and these are the 4 nodes. And this is the element E. For this, we have capital I, J, K, and L. We are naming them as I, J, K, L as our, let's say, like this. This is the element connectivity which has been done. See, for each local node I, we assign the 3 degrees of freedom, and the Q3, this the way we are writing them. For example, if you take node 2, how this is that? See, if you look at this, Q4, Q5, and Q6, if you see that. So this is like, if you call this as the I, then this will be, it will be Q3I minus 2, Q3I minus 1, and Q3I. You can see here, this is node 1 is 2, 2 into 3, 6 minus 2 is 4, 6 minus 1 is 5, 6 is 6 only, like this. So this is as far as what you call it, the element nodal connectivity is concerned. Even for global connectivity also you are going to write the same thing. That is, if you have the global node number I, then it is Q3I minus 2, Q3I minus 1, and Q3I. You can write it in this particular fashion, and you can get this. But only interesting point is, you remember, when it comes to the element displacement matrix, it will remain like this. But when it comes to the global, you can say nodal vector, it is depends upon the total number of nodes and the total number of degrees of freedom associated with that. So it will be going up to n. It depends upon the total number of nodes which are present in the entire structure, and into multiply by, you can say, 3 for every node. Automatically it will give you the total Qn. It is the total number of okay. So this is about what you can say, the degrees of freedom associated with that. Where capital N is the total number of degrees of freedom. Total number of degree of freedom. Total in the entire structure. This is, of course, it is in the structure. This is all for the structure. Whereas for element, these are the 12 nodal displacements. This is for element level. This is at the element level, and this is at the, you can say, total number of degrees of freedom for that. See, here we define 4 Lagrange type shape functions. Okay. See, what we have studied in the earlier class also, this is called Lagrange type shape functions, where n1 is given by zeta, n2 is given by theta, n3 is this one, and n4 is 1 minus, it is not independent, it is dependent on these 3 coordinates. Okay. So these are the 4 shape functions which are going to be defined for a tetrahedral element. Like in the case of a triangular element, we had seen these 2 were there and this was there, and these 2 were not there. But in the 3-dimensional tetrahedral element, 4 shape functions are there because 4 nodes are there, and these are going to be defined in this particular manner. So if I take one master element, and if I define the nature of variation of these natural coordinates along that, how it looks, let us see quickly. This is the origin, 4th node. When it comes to 1, 1, 0, 0. When it comes to 2, 0, 1, 0. When it comes to 3, 0, 0, 1. And you are already knowing n1 is zeta, n1 is theta, n3 is theta, n4 is 1 minus theta, theta. This is going to be the formulation what you are going to get this. And you are already knowing the interesting part. What you have to remember here is u. See, when it comes to u, look at that. What are those? Obviously, you look at this. In the x direction, in the u direction, there is q1. Then directly there is a q4. Then there is a q7. Then there is a q10. So there are 4 components which are there. Therefore, we will write it as n1 q1 plus n2 q4 plus n3 q7 plus n4 q10, like that. So you can even define v also. It is n1 q2 plus n2 q5. You have to go on adding maybe what, like, yeah, v2, correct. It is v component is going to be added with q5. Then another 3, that is N3Q8 and N4Q11. This is going to be this one. So in the last W is given by N2Q3, N2 all of them, and if you write these, that is U vector, if you want, this will be written as N1 0 0 0 N1 0 N2 0 0 0 N2 N3 0 0 0 N3 0. Okay, so now this is the yes, this is going to be the shape function, and these are of course Q1, Q2 up to Q12. You can get this. So all this you can write it as U is equal to NQ. You can write this is the general expression for the displacement vector in terms of the nodal displacement vector. If you want to find out anything, you can directly find out. And at the same time, we know the isoparametric formulation applies here also. That means you can use the same shape functions even to predict the coordinate of the interior point. For example, if you know that x1, y1, x2, y2, x3, y3, x4, y4, if these are the nodal coordinates of these 4 nodes, and if you take the interior point, let us say B or something like that, if you want to relate these x with the other coordinates of this thing, I can use same thing. That is, this is isoparametric formulation. Transformation. This is called isoparametric transformation. That is, we can relate x equal to what? X will be equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Similarly, if you want y, it is n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. Okay. In the similar way, if you want z also, n1 z1 plus n2 z2 plus n3 z3 plus n4 z4. This you can very well use for transformation, and we had used in the case of triangular elements and all that, I had written the notation Kij is equal to Ki minus Kj, Yij is equal to Yi minus Yj. This is the notation we had used. Of course, here for Z also you will get Zij equal to Zi minus Zj. So if you substitute all these shape functions into this equation, what you will get to tell me? These will be converted into x equal to x4 plus x14 zeta, x24 eta, x34 zeta. Similarly, y equal to y4 plus y14 zeta, y24 eta, y34 etc. And z is equal to z4 plus z14 zeta plus z24 eta plus z34 theta. This is the way we can write down all these things. And in the similar manner, you are already knowing the partial derivatives between this. Well, suppose if I take u components, dou u by dou zeta, dou u by dou eta, and dou u by dou theta. These are all equal to the Jacobian matrix we have already seen in the earlier case. This is equal to dou u by dou x, dou u by dou y, and dou u by dou z. This is what you have seen. And I have told you J, that is Jacobian of transformation. What is this J? J is given by dou x by dou zeta, dou y by dou zeta, dou z by dou zeta. Similarly, dou x by dou eta, dou y by dou eta, dou z by dou eta, dou x by dou theta, dou y by dou theta, dou z by dou this one. Okay, this is all right. And you know from this coordinates from here, you can easily make out what is this. x14, y14, z14, x24, y24, z24, x34, y34, z34. This is a 3 by 3 matrix. Of course, the determinant of this is what? When you take this into this minus this into this, minus 1 raised to n, this equal to this into this into this you have to take. When it comes to this into this into this, that you have to take. So let us quickly write what is the determinant of J. If I want to write the determinant of J, it is equal to x14, y24, z34, y34, z24 plus y14 into bracket z24 x34 minus z34 x24, and lastly z14 is equal to x24 y34 minus x34 y24. So this will give you the determinant of the Jacobian matrix. And you are already knowing that in 2D we used to call, to find out the area of the triangle, we used to take it as half of the determinant of J. But in this case, since the three-dimensional analysis is involved, here the volume is involved. So here we need to find out the volume of the element, not the area of the element. We need to find out the volume of the element for that. So we'll just quickly note that. Okay. Now, as I mentioned you, I will be discussing about what you call it as the volume of the element is given by the volume of the element, okay, is given by V, is equal to integration 0 to 1, integration 1 minus zeta, 0, 1 minus zeta minus theta, determinant of j, d zeta, d eta, d this. Since the determinant of j it is a constant, I can find out this volume of element is equal to, I can take the determinant of j, since it is a constant, I can directly write 0 to 1, 0 to 1 minus zeta, 0 to 1 minus zeta minus theta, t zeta, t eta, d this one. This is what we can call it as the volume. But here, using the polynomial integral formula, using the polynomial integral formula, because here we have to evaluate the volume in terms of that. The general formula given for this is 0 to 1, 0 to 1 minus zeta, 0 to 1 minus eta minus eta, zeta raised to m, eta raised to n, and this raised to p into d zeta, t eta into d eta. This is given by factorial of m, n and p. This is the factorial of all the three, plus m plus n plus p plus 3 for each degree of freedom, and again factorial of that. So if you use these, of course here there are no m and zeta and all that, these are 0, 0, 0. So if you substitute that and if you do that, what we will get is, actually what we will get is the volume of the element is coming 1/6 of the determinant of j, it is going to come this. So naturally when we want this particular expression for finding the strain components, what we need is these. So obviously I have to take j this side and I have to take the inverse of the Jacobian matrix. As we did in our triangular elements, we have already taken the inverse of the Jacobian matrix and then we multiplied with all the zeta components and all that, and then we found out the strain matrix, and before that we found out the strain displacement matrix BQ, epsilon is equal to PQ, and we derived that. So now also here we will do the similar thing, similar analysis we will do. So here yes, we will take the inverse relationship corresponds to this, that is dou u by dou x, dou u by dou y, dou u by dou z. And if you look at this we call it as A matrix, because what is A I will give you in detail, which is nothing but the inverse of the Jacobian matrix, dou u by dou zeta, dou u by dou eta, and dou u by dou this, like this, where A is the inverse of the Jacobian, inverse of the Jacobian matrix. Okay, that is what you call it as J inverse, and this is given by 1 upon determinant of J into bracket y24 z34 minus y34 z24. Okay, this is going to be a bigger equation. y34 z14 y14 z34 y14 z24 minus y24 z14. Okay, when it comes to this second one, Z24 X34 X34 Z34 X24 Z34 X14 Z14 X34 Z14 X24 minus Z24 X14. The similar way, X24 Y34 minus X34 Y24. This is again X34 Y14 minus X14 Y34. So really here X14 Y24 minus X24 Y14. Yes, this constitutes the inverse of the Jacobian matrix, what we get. So with this, now since you know that the displacement vector is related to the displacement of at the nodes by u equal to nq, and with the substitution of all this, I will be getting a 6 by 12 element strain displacement matrix B. I will get. So let me write that. That is going to be a very big expression. We will just copy that. Here it is more of, you can say, copy, because all the expressions are in mathematical nature. I just cannot dictate you on video now. So I need to write, and so that you can just read these elements and you can copy down in a paper and you can practice this. Because they can always ask to derive the element strain displacement matrix for a tetrahedral element, right? See, as you are already knowing, the strain is nothing but B into Q, and using those J inverse as well as those dou U by dou Z and all those things after multiplication and all that. So what finally you will get is a P matrix, element strain displacement matrix. B, which is going to be a 6 by 12. It's a very big one. A11 000. Maybe we can write the horizontal line so that we can write them in the same line. Yes, this is going to be 12 lines are needed. The zeros A31, A21, 0, A21, 0, A31, 0, A11, 0, 0, A31, A21, A11 and 0, A12, 0, 0, 0, A32, A22, right, exactly, 0, A22, 0, A32, 0, A12. 0, 0, A32, A22, A12 and 0, A13, 0, 0, 0, A33, A23, 0, A23, 0 A33 here, then 0 A13. Okay, then comes the 0 0 A33. Yes, this is A00 A33, and then 0. Yeah, 0 0 A33, A23, A13, and then yeah. Next interesting is this will be considered as A1 hash here. What is that? I will explain you. Another two zeros are going to come, so this is going to be extended up till here. All this, and then the real bracket is going to come here now. Now this is going to be 0 minus A2 hash, 0 0 0 minus A3 hash, 0 minus A3 hash minus A2 hash, then minus A3 hash, 0 minus A1 hash minus A2 hash minus A1 hash, and 0, where A1 hash it is equal to A11 plus A12 plus A13. Similarly, A2 hash, A21 plus A22 plus A23, and A3 hash is A31 plus A32 plus A33. Please remember, all the terms in B are constants, so therefore it is going to be a constant matrix. So therefore the stresses and the strains are going to be remaining constant throughout this. So it is one another same as what we developed for constant strain triangle. Also we found that B matrix was full of constants. So therefore overall, when we looked into the complete B matrix, it came out to be constant. So therefore the strains will automatically remain constant, and correspondingly the stresses will remain constant at the various points. So now let us consider quickly how to find out the expression for the element stiffness matrix. Okay, quickly we will write that for element stiffness matrix, which we can call it as KE, okay, like this. So as you know it, always we start with the element strain energy. Element strain energy is the one we always start with for deriving the element stiffness matrix. This is equal to, it is transpose C and epsilon into dV it was, the original one. Now if you substitute, sigma is equal to C epsilon, or sigma transpose equal to epsilon into C. This is what we know. So this is over the volume, epsilon transpose C epsilon into dV. These are all, of course, vectors. These are not single terms. These are all matrices or vectors, you can call it. And since you know E transpose equal to B into Q, because already you know epsilon is equal to PQ, and the transpose of epsilon is Q transpose B transpose. Okay. So if I substitute this in this equation, and if I take the other one constant, then the integration of dV, when I take here, it is the volume of the element only. This is going to come as the volume of the element. So therefore what I will do is half 0. Okay. Okay, what we will do is this, I will take Q transpose B transpose. I will take here. This is going to be B and this is going to be, yes, BQ it is for the epsilon. And this integration sign, if I put here, this will be here and then this is going to come here. Or you can interchange here also. You can write this dV here and then you can write Q here. So if you take all these things, what is going to come? Tell me. Half Q transpose. This is going to come VE, this element, whatever is that. Then B transpose CP into Q will come. So if you look at this whole thing, this is nothing but half Q transpose K into Q, because this is the element stiffness matrix. You know, famous equation for element stiffness matrix from the strain energy is always half Q transpose KQ. So therefore, the element stiffness matrix as such comes, it is VE, B transpose C into B, where VE is the volume of the element. How you are find out? I have already showed you. This will be 1/6 of the determinant of J. This is obtained by 1/6 of determinant of J. You can find out that, and you can find out all this matrix, which is going to be a very big calculation. By hand calculation, it is very difficult to do that. Generally, this is done in computer applications with the help of software. So, what is going behind in any CAD package is, this is what you will be calculating. It is going to be, well, look here, it is 6 by 12 it was there, therefore it is going to be 12 by 6, 6 by 6, then 6 by 12. So therefore it is going to be, since there are totally 12 degrees of freedom associated with what you can say, all the 4 nodes. So obviously the size of the element stiffness matrix is going to be of 12 by 12. Okay. So this is about what you call it as the element stiffness matrix. Then comes the force terms. We'll quickly study about the force terms. There are 2 force terms. One is the body force, another is the traction force and the point load. Okay, now let us take the force terms. That is first body force. Integration U transpose F into dV, which you are already aware. U is what? U, V, W, and these are Fx, Fy, Fz into dV. And U itself, you are already knowing N1, Q1 and all that you know. So, when you substitute all these things into this, what finally you will get? Since it is over the volume you have to integrate, naturally there will be triple integration. It will come with the triple integration. First, as usual, Q transpose will come triple integration N transpose F, and the volume is written as determinant of J d zeta t eta m. So that, which you can write it as Q transpose Fe. This is the body force vector. This is different. This is consisting of all whatever is that. So all together the product of this will be our this. So where after integration, this body force vector for every element, how the load is getting distributed is VE upon 4 into bracket Fx, Fy, Fz. For all the 4 nodes, Fx, Fy, Fz, Fx, Fy, Fz, Fx, Fy, Fz. So all these, you can say, three components in M, all the things will be equal. V by 4, total volume upon 4. 1/4 of the total volume is going to be body force is going to be distributed in all the 3 directions of the nodes. Or you can see that. So naturally, this is going to be of what size? See, totally it is 12 by 1 size. All these 12 components in respective x, y, z directions, it is going to be there, and then we are going to find out the total body components. In the similar way, we can find out the traction force also. So second, if I take traction force, this is going to be along the area. Please remember, here it is not along the edge. It is distributed on a triangular area. So therefore, we talk about over the area we have to integrate this. U transpose T into dA will come into picture. Whereas this will be again when I substitute this integration over the area, of course, N transpose into T into dA, which will give you Q transpose TE, where TE AE by 3 very interesting thing is here, Tx, Ty, Tz will come, Tx, Ty, Tz, it is at the second node, Tx, Ty, Tz. So can you tell me what will come here? Because when you look at the load distribution on a particular figure, if you look at this, let us say 1, 2, you can take 1, 2, 3, 4, if you take like that. If you consider only one of the face, for example here, this is going to be there like this. Okay. So obviously, there is no, this load distribution or this traction is taking place on this face. So therefore, this contribution is going to be distributed only on the 3 nodes. 4th node is isolated. There is no influence of the distributed load on the 4th node, because that is the reason that if you look at the 4th component, what it should be ideally? It should be 0, 0, 0, because we don't have any contribution of the you can say traction force over that. See, once you have formulated the element stiffness matrix, then you have written for all the elements, then maybe you are going for global stiffness matrix by taking into account all these forces. Of course, the point force will remain same. Wherever the nodes at which the point load is acting, they are all summed up with the corresponding displacements. So that's why UI transpose PI, you will get that. Depends upon which components of forces, X or Y or Z, Px, Py, Pz. These are the 3 components of forces which are acting at a node. And if you multiply by U into Px, V into Py into W into Pz, then that will give you the total summation of the influence of the point load. And then when you club up all the influence of body force, traction and the point loads into the global vector, then the very famous finite element equation, which is the KQ is equal to F, will be formed, and with appropriate boundary conditions and all that, you can finally reduce this and get all the nodal displacements of the entire structure, Q1, Q2, Q3 up to Q1 you will get. Once you know that, then you can calculate the stresses in the members. Here we are getting stresses in terms of stress invariance. Here it is not the simple way what we have done in our earlier analysis. So we need to calculate what are called as stress invariance. So that part I think I will take it tomorrow, and we'll discuss about the